So welcome back guys. Today is the last lecture of this course and we will be discussing one last application within application of group theory to spectroscopy, which is spectral transition probabilities and symmetry based selection rules. So we have done a brief discussion on this when we were discussing direct product applications, right? So where we actually looked at whether a particular transition moment integral will survive or not based on, so we'll see that and then we'll go into more details of what spectral transition probabilities are and how do we calculate exactly those probabilities using group theory rules. Okay, so let us start with the spectral transition probabilities. And in this we will be discussing symmetry based selection rules. So we have already seen that various normal modes of a molecule can be catalogued using group theory, right? And we can also analyze whether what will be the symmetry of those normal modes and all. But now whether we can observe those vibrations in IR and Raman spectra, because IR and Raman spectra are the one where we are expected to see such vibrational modes, right? So the question is, can we observe all the vibration modes in IR and Raman spectroscopy? Okay, so how do we do that? So we know what the selection rule is. We know that the change in vibrational quantum number should be plus minus 1 and only these transitions are allowed, right? So we can say V is equal to 0 to V is equal to 1 transition is allowed and so on and so forth, like 1 to 2, 2 to 3 and so on and so forth, right? So pictorially you can see that if this is my simple harmonic potential surface and this is V equal to 0, V equal to 1, then this transition is allowed, right? So this transition is allowed transition. Now if I want to write the transition moment integral for this we have already seen, so I'm just repeating this, but we will go into more details of this. So transition moment integral, we can write it as m 0 to 1 will be given by psi of 0 mu and psi of 1 to star and d tau, and this should not be equal to 0 for a transition, we can say for allowed transitions. Okay, now the intensity of the spectral line, we can also measure the intensity, we can say proportional to, not equal to, will be proportional to the square of this integral mu. So this is the intensity, but of course you need to know the exact form of these psi wave functions, which we'll also discuss today. Spectral lines, so we know psi 0 and psi 1 are the wave functions of ground state and first excited state, vibrational state. And what is mu? So mu is, again we have seen this earlier, mu is oscillating electric dipole moment vector as a function of the normal coordinate of the normal mode. So what is normal coordinate of the normal mode? Let us also look that. So let's define this quantity normal coordinate by q. So normal, we can say q is a single reference coordinate by which the progress of the normal mode is followed. So how that particular vibration is changing the bond length, for example, that is followed by a single reference coordinate which is called as normal coordinate. So let's say a diatomic molecule AB, the normal coordinate is in terms of the displacement of the two atoms, because that will lead to the stretching or compression of this bond, which is one of the vibrational modes, right? Displacement of the two atoms, as we can write as delta RA plus delta RB. So how much A is moving from its mean position, how much B is moving from its mean position, that is called as delta RA and delta RB, and the total sum of that will be called as Q. So Q is a normal coordinate to define that particular normal mode, which is the vibrational mode, right? So every vibrational mode can be expressed in terms of a normal coordinate, which is a single reference coordinate. So what is the idea behind it? So idea is that the symmetry of the normal mode. So if we, why are we doing this? So symmetry of the normal mode, which we already know from character table, right? We have learned in last lecture how to find out the symmetry of normal mode, is equal to, is same as symmetry of the corresponding normal coordinate. Again, we will see why we need the symmetry of the normal coordinate. It will come in the Hermite polynomial later. But so idea is that symmetry of the normal mode, which we already know, we have seen in last lecture. How do we find out symmetry of normal mode? Is basically same as the symmetry of the corresponding normal coordinate. So symmetry of Q is same as the symmetry of the corresponding vibrational mode. Okay, so now let's see what is mu. So now mu has three components. That also we have learned earlier, right? You can express mu as summation of mu x, mu y, and mu z. And basically mu is nothing but summation of charges present at different Cartesian coordinate values, right? So you have xi over I, summation of all the charges and their corresponding distance from origin, let's say ei yi I summation ei zi I, right? So that's why mu can be expressed as mu x, which is this part, mu y, which is this part, mu z, which is this part, right? Now if mu has three components, so then the transition moment integral will also have three components, right? So you can say that the mx is psi 0 mu x psi 1 star d tau Similarly, my is psi 0 mu y, and psi 1 star theta mz is equal to psi 0 mu z psi 1 star theta. Now if any of these three is non-zero, then the overall m will be non-zero, and thus the integration or the transition moment integral will be non-zero. That means the transition will be allowed, right? So you need to find out all three, and if any of these three survives, then you have a allowed transition, right? Okay, so now when I say this integral, let's say if I'm talking about mx psi 0 mu x psi 1 star d tau. So I need to know, if you remember the direct product applications, so I need to know the corresponding IR representation for psi 0 mu x y z and psi 1, right? All three we must know, and then only we should be able to find out those corresponding IR representation and find out the direct product of all three. And that direct product, if it corresponds to, if it contains totally symmetric representation, the integral will be non-zero, right? Remember that, right? Okay. So now how do I find out what is the IR representation for this psi 0 and psi 1? So we have discussed few examples earlier where it was given to you that psi 0 is this and psi 1 is this. But now let's say if we want to know how do we identify what will be IR representation. So let us see what is the wave function of a normal mode. So wave function of a normal mode, or of normal modes in general, we can say. So we can say wave function of normal modes can be written in the simplest way using the normal coordinates, which we have just learned what is normal coordinate. So if we know the symmetry of normal coordinates, we can back calculate the symmetry of wave function, right? So that means we should know the symmetry of the normal mode, and correspondingly symmetry of the normal coordinate can be predicted, and from there the symmetry of wave function can be predicted. Okay, so now let's see normal coordinates as the variables, and this will be assuming simple harmonic oscillator model. So we can write down any general wave function psi I n can be written as ni exponential of minus alpha I by 2 and qi square hn. See, I'm not asking you to remember this expression, I'm just giving you this expression, and if I ask in exam I will give you this expression, so do not worry about it. It's a long expression, I know, but just understand the maths behind it. Okay, now where ni, so let us try to explain all of this. So psi I is the wave function of the normal mode. Ni, this ni is normalization constant, so it does not affect the symmetry. Now what is the next one? Alpha I. Alpha I is 2 pi nu I by h, where nu I is the frequency of ith normal mode. So now next is qi. So qi is ith normal coordinate. We just learned what is normal coordinate. And how is this expressed? This is expressed as SALC of internal displacement coordinates. Basically how the atoms are moving, so there that will be internal displacement coordinates. So a linear combination of internal displacement coordinates gives you a particular qi, which is normal coordinate of that particular normal mode, right? We have already seen this example. Now hn is Hermite polynomial of order n. We will see what that is. N is a vibrational quantum number. So if you are talking about ground state, n will be 0. Quantum number. Okay, let's see how do we write hn. Hn can be written as hn of x, let's say, is minus 1 to the power of n e to the power of x square nth derivative dx n e to the power minus x square. So, and first few Hermite polynomials are, so let's try to write down. So h0 of x is 1, h1 of x is equal to 2x. You can calculate it yourself, it is easy. I'm just giving you first few so that we don't need to calculate every time. Then h2x is 4x square minus 2, h3x is 8x cube minus 12x. Okay, so if you see, there is a trend. It is even for even values of n, right? And it is odd for odd n, right? That trend can be seen. So n equal to 0, the function is even. N equal to 1, the function is odd. N equal to 2, the function is even again. N equal to 3, the function is odd again, right? So all we care about whether it's even and odd, because we are talking about the integration and we are interested in symmetry. We are not exactly interested in what is the functional form of this. Now let's try to calculate the symmetry of ground state. Okay, because let's say if we are interested in ground state and the first excited state, so of course you can calculate for the second excited state, third excited state. All those calculations can be done. Let's try to calculate for psi I0, right? Ground state. So psi I0 is equal to Ni e to the power minus alpha I by 2 and qi square h0 x is alpha I square root of alpha I and qi. Now it does not matter what x is, h of 0 goes to 1. So this quantity is equal to 1, right? And now we are left with this quantity. Okay, so what is this over here? Let's see. So you have psi I 0. So you are left with ni e to the power minus alpha I by 2 and qi square, right? So this thing goes to 1. So we are left with only this. So now let's see what is the symmetry of psi I. So we know the symmetry of qi and we know the symmetry of qi square. So we'll know the symmetry of psi I. Let's see how to do that. So now for qi as a non-degenerate, or we can say one-dimensional IR representation. See, the IR representation for qi will be same as the IR representation for the corresponding normal mode, right? So we have seen that the symmetry of normal mode is equal to symmetry of the normal coordinate. So we know this will have symmetry of the normal mode. Now that symmetry can be one-dimensional or two-dimensional. It can be non-degenerate, which is 1D IR representation, or it can be degenerate and then it will be a 2D IR or 3D IR representation, right? We have seen that normal modes can have symmetry of 1D IR and 2D IR and 3D IRs. Okay. So now if it is a 1D IR representation, non-degenerate vibrations, we can say all symmetry operations will have character as plus minus 1, right? In any 1D IR representation, the character is always plus minus 1, right? So if this is plus minus 1, so the square of qi will have characters as plus 1, only plus 1, not minus now, right? Only plus 1. So this is to remember, it's only plus 1. So what does that mean? That means qi square will always form basis of totally symmetric representation, right? In most cases it is A1 or A, right? So this is for a non-degenerate case. Now let us look for a degenerate case. In a degenerate case, we will also discuss examples, so do not worry about if you're not able to follow it. We'll see examples and then it will be very clear. So in a degenerate case where QA and QB, let's say there are two Q values for the corresponding degenerate case, are two normal coordinates of a pair of vibrations. Now degenerate vibrational mode, that means two vibrations will have same frequency. Now those pair of vibrations will have two normal coordinates QA and QB, right? Now any symmetry operation on, let's say, R operating on QA will have following result. So if you operate R onto QA, what you will get is you will get a linear combination of QA and QB. Why linear combination? Because both of them are forming the basis of that particular IR representation, right? It's a degenerate representation. So for example, if you apply C3 on X, and if X and Y together are forming basis, you will get X plus Y, some combination of X and Y, right? RA and RB will be those coefficients, right? So you can say that this is my Q prime, right? Let's say. So this is linear combination of orthogonal functions which together form the basis for a particular IR representation. And R is symmetry operation, right? So this is understood. Now let's say, since my normal coordinates are orthogonal and normalized, since normal coordinates are orthogonal and normalized, I can say QA square is equal to 1 and QB square is also equal to 1. And then my RA and RB are such chosen so that Q prime square is also equal to 1, because this also has to be normalized, right? This is the normalization condition. So Qi square is also 1. So that means whatever is the value of Qi, like if I'm operating symmetry operation onto Q prime, so if I square this, I will always get 1, right? So thus, in degenerate case also, psi I 0 remains invariant under any symmetry operation. This should be clear now. So that means it will form, so psi I 0 will always form basis for totally symmetric representation, right? So whether it is 1D or 2D, so it will always form basis for psi I 0 will always form basis for totally symmetric representation, right? So now we know the IR representation for psi I 0. Now let us calculate for the excited state, psi I 1. So for vibrational excited state, psi I n has the symmetry of nth Hermite polynomial, right? Other than that, it is not, and nothing is contributing into the symmetry. So let's see how it happens. So for first excited state, let's say for first excited state, so we have n equal to 1. So psi I1 can now be written as q e to the power minus alpha q square divided by 2, right? So this q is coming from the Hermite polynomial after solving for n equal to 1. Now that means, so q square is nothing but, q square is totally symmetric representation, so this does not contribute to symmetry. Now the symmetry contribution comes from q. So whatever is the symmetry of the normal coordinate, that will be the symmetry of the first excited state, right? So the symmetry of normal coordinate is coming from symmetry of the corresponding normal mode. So that means the first excited state will have symmetry of the normal mode itself. Okay. So let's say symmetry of normal mode, which is determined in last lecture, is equal to symmetry of normal coordinate Q, and this is equal to symmetry of first excited state. So this is clear.